welcome to this problem walkthrough. Today, we'll be diving into LeetCode problem number 2091, removing minimum and maximum from array. In this problem, we'll explore how to calculate the minimum number of operations needed to remove the smallest and largest elements from an array. Let's get started. In this problem, we are given a zero-indexed array called nums that contains n distinct integers. Our goal is to remove both the minimum and maximum elements from this array, but we have specific removal options to consider. These options include removing both elements from the front of the array, removing both from the back, or removing one from the front and the other from the back. The task is to determine the minimum number of moves required to remove both the minimum and maximum elements, where a move is defined as removing one element from either end of the array. The input to the problem consists of a single array, and the output is an integer representing the minimum number of moves required. To understand this problem better, let's look at the first example. Here, the input array is nums equals 2, 10, 7, 5, 4, 1, 8, 6. The minimum element is 1, located at index 5, and the maximum element is 10, located at index 1. One way to remove them is by first removing the maximum element at index 1 from the front, which takes 1 move, and then removing the minimum element at index 5 from the back, which takes 4 more moves. In total, this approach requires 5 moves. This illustrates how the minimum and maximum elements can be removed efficiently by considering their positions in the array. Now, let's examine another example. Here, the input array is nums equals 1, 2, 3, 4, 5. The minimum element is 1, located at index 0, and the maximum element is 5, located at index 4. In this case, we can remove both elements in just 2 moves by taking the minimum from the front and the maximum from the back. This is the most efficient approach since both elements are already at the ends of the array. By minimizing the number of moves, we ensure the solution is optimal. In the final example, the input array is nums equals 4, 3, 1, 2, 5. The minimum element is 1, located at index 2, and the maximum element is 5, located at index 4. Here, one efficient strategy is to first remove the maximum element at index 4 from the back, which takes 1 move, and then remove the minimum element at index 2 from the front, which requires 3 moves. This results in a total of 4 moves. The problem also comes with constraints to ensure efficiency, such as the array size being up to 10^5 and all elements being distinct. Edge cases include arrays with only 2 elements, where the result is always 2 moves, or scenarios where the minimum and maximum elements are at extreme positions, which can influence the optimal strategy. To tackle problem number 2091, our goal is to determine the minimum number of operations needed to remove both the smallest and largest elements from the array. Since there are multiple ways to achieve this, efficiency becomes key. Let's start by considering a brute force approach. The idea here is straightforward. We first find the indices of the minimum and maximum elements in the array. Once we have these indices, we evaluate 3 possible strategies for removal. The first strategy is to remove all elements from the left up to the farthest of these 2 indices. The second strategy is to remove all elements from the right up to the farthest of the 2 indices. Finally, the third strategy involves removing one index from the left and the other from the right. After computing the costs of these 3 strategies, we simply return the smallest value. While this approach is simple to understand and implement, it doesn't leverage deeper optimizations, which can make it less appealing for very large arrays. A more efficient solution comes from an optimized 2-pointer approach. Instead of manually removing elements one by one, we compute the minimum number of operations directly using the indices of the smallest and largest elements. Here's how it works. First, calculate the cost of removing all elements from the left up to the farther of the 2 indices. Second, compute the cost of removing all elements from the right starting from the closer of the 2 indices. Third, determine the cost of removing one index from the left and the other from the right, or vice versa. Once we have these 3 values, the smallest among them is our answer. This approach improves efficiency by focusing only on the key indices, avoiding unnecessary computations. With a time complexity of O(n) and a space complexity of O(1), it's both fast and space efficient. However, it assumes the array is small enough that finding indices directly is feasible, which is a reasonable assumption for this problem. Now, the key insight here is that this problem essentially boils down to comparing three straightforward removal strategies. Once we identify the indices of the smallest and largest elements, the rest of the solution is just simple arithmetic. By avoiding direct manipulation of the array, we save on computational cost, making this approach even more efficient. While the brute force method is conceptually easier, it doesn't scale well for larger arrays due to its lack of optimization. On the other hand, the optimized two-pointer approach, though slightly more complex, is elegant, efficient, and maintains minimal space usage since no additional data structures are required. This trade-off makes it the ideal choice, as it balances simplicity, efficiency, and scalability. Ultimately, the two-pointer strategy allows us to solve the problem in a clean and optimized manner, making it the most practical solution for this challenge. In this problem, our goal is to determine the minimum number of operations required to remove both the smallest and largest elements from an array. The operations allow us to remove elements either from the left end or the right end of the array, and there are multiple strategies to achieve this. To solve the problem efficiently, we start by identifying the indices of the smallest and largest elements in the array. This can be done in a single pass through the array, which means we only need n time for this step. These indices are crucial because the optimal removal strategy depends on their positions, whether they are near the same end of the array, far apart, or somewhere in between. By focusing on these indices, we can determine the most cost-effective way to remove both elements. Next, we compute the removal costs for all possible strategies. There are three main ways to remove the smallest and largest elements. First, we can remove all elements from the leftmost index up to the farthest of either min_index or max_index. The cost for this approach is the maximum of these indices, plus 1. Second, we can remove all elements from the rightmost index back to the farthest of the two indices, and the cost here is the total length of the array minus the minimum of min_index and max_index. Lastly, we can remove one element from the left and the other from the right. For this case, there are two sub-options, removing the smallest element from the left and the largest from the right, or vice versa. Each approach has its own cost formula, and we calculate these values to find the minimum cost among all strategies. Once we have evaluated all four cases, we return the smallest cost as our result. The key to solving this problem lies in recognizing the optimal removal strategy based on the relative positions of the smallest and largest elements. When both indices are close to one end of the array, it is generally more efficient to remove elements from that end. However, if the indices are far apart, removing one element from each end might yield a lower cost. This flexibility is essential because the array is unordered, so we must evaluate all options to ensure we find the minimal cost. The algorithm is efficient, it runs in n time because finding the minimum and maximum elements requires a single pass through the array, and the cost calculations involve only a few constant-time operations. Additionally, we use simple data structures, like the input array to store elements and variables to keep track of indices and intermediate results, ensuring both simplicity and speed. Now, let's consider some edge cases. If the array has only one element, the problem guarantees that such cases don't exist, as the smallest and largest elements are the same. For arrays with two elements, the cost is always 2 since we remove both elements directly. When the smallest or largest values are duplicated in the array, we only consider the first occurrence of each value when determining the indices. Let's apply this to an example with the input array 2, 10, 7, 5, 1, 8. Here, the smallest element is 1, found at index 4, and the largest element is 10, found at index 1. These indices will guide our cost calculations in the next step. Using the indices we just found, we calculate the costs for each removal strategy. First, removing from the left only requires removing up to index 4, so the cost is max 1, 4, plus 1 equals 5. Removing from the right only requires removing back to index 1, so the cost is 6 min 1, 4 equals 5. For the two strategies that involve removing from both ends, the first option removes the smallest element from the left and the largest from the right, resulting in a cost of 4 plus 1 plus 6 to 1 equals 10. The second option removes the largest from the left and the smallest from the right, with a cost of 1 plus 1 plus 6 to 4 equals 4. Among these, the minimum cost is 4, so the output for this example is 4. Let's walk through the solution step by step. The goal is to find the minimum number of deletions required to remove both the smallest and largest elements from the array. 1. Input size and edge case handling. Since the input array nums always has at least 2 elements, according to problem constraints, we directly proceed with the solution without additional checks. 2. Finding indices of minimum and maximum elements. We first calculate the indices of the smallest, minimum, and largest, maximum, elements in the array using the min and max functions. These indices will help us determine which removal strategy is optimal. 3. Sorting indices for consistency. To simplify calculations, we ensure min_index and max_index are sorted such that left is the smaller index and right is the larger index. This allows us to evaluate removal strategies in a consistent manner. 4. Evaluating removal strategies, we consider 3 possible strategies. Strategy 1. Remove all elements from the left up to the right index, inclusive. This requires right plus 1 deletions. Strategy 2. Remove all elements from the right up to the left index, inclusive. This requires n left deletions. Strategy 3. Remove elements from both ends. This involves removing elements from the left up to left index and from the right up to right index. The total deletions required are left plus 1 plus and right. 5. Returning the optimal result. The minimum number of deletions among the 3 strategies is calculated using the min function. This value is returned as the result. By evaluating all possible strategies, this approach ensures the solution is optimal. The time complexity is O(n), as we only perform a single pass to find the indices and evaluate strategies. The space complexity is O(1), as no additional data structures are used. This code is clean, efficient, and handles all edge cases within the problem's constraints. Here, we start by importing the necessary utilities and defining our solution class with the method minimum deletions. The goal of this method is to determine the minimum number of deletions required to remove both the smallest and largest elements from the given array nums. First, we calculate the length of the array and initialize 2 variables, min_index and max_index, to track the indices of the minimum and maximum elements, respectively. Using a loop, we iterate through the array to find the actual indices of these extreme values. If we encounter a value smaller than the current minimum, we update min_index, and similarly, if we find a value larger than the current maximum, we update max_index. After identifying these indices, we ensure consistency in our calculations by determining the smaller of the 2 indices as left and the larger as right. With these indices in place, we can now begin to evaluate different strategies for removing the elements. The first strategy, remove from left, considers removing all elements up to the right index, inclusive. This represents the case where we delete from the start of the array up to the furthest of the 2 indices. Next, we explore an alternative strategy, remove from right, which involves removing all elements from the end of the array up to the closest of the 2 indices, represented by left. This approach essentially deletes from the back of the array towards the smaller index. Additionally, there is a third strategy, remove from both, where we remove elements from both ends of the array. Here, we count the number of deletions required to remove all elements from the start up to left and from right to the end of the array, combining these 2 counts. Finally, to determine the optimal solution, we return the minimum value among these 3 strategies using the math.min function. This ensures that we select the approach requiring the least number of deletions, effectively solving the problem while keeping the implementation clear and efficient. Here, we are starting with example 1, where the input array is nums equals 1, 3, 5, 2, 7, 9. The length of the array, n, is 6. The first step is to identify the indices of the minimum and maximum elements. The minimum value in the array is 1, which is located at index 0, while the maximum value is 9, found at index 5. Next, we normalize these indices by determining the smaller of the 2 indices, which we call left, and the larger of the 2 indices, which we call right. In this case, left is 0, and right is 5. Once we have these indices, we calculate 3 possible strategies for removing the minimum and maximum elements. The first strategy is to remove all elements from the left up to the furthest index, giving us a total of 6 deletions. The second strategy is to remove all elements from the right, starting from the closest index, which also results in 6 deletions. The final strategy is to remove elements from both ends, which requires 2 deletions. The next step is to determine the minimum number of deletions needed. We compare the results from the three strategies we calculated earlier. Removing from the left gives us 6 deletions, removing from the right also requires 6 deletions, and removing from both ends only requires 2 deletions. The minimum of these values is 2, which becomes our final output for this example. Now, moving to example 2, the input array is nums equals 10, 20, 40, 30, 50, and the length of the array, n, is 5. The minimum value in this array is 10, located at index 0, and the maximum value is 50, found at index 4. We normalize these indices in the same way as before, with left being the smaller index, which is 0, and right being the larger index, which is 4. In this example, we again calculate the three strategies for removing the minimum and maximum elements. Strategy 1 involves removing all elements from the left up to the furthest index, which requires 5 deletions. Strategy 2 involves removing all elements from the right, starting from the closest index, which also requires 5 deletions. Strategy 3 involves removing elements from both ends, which only requires 2 deletions. To find the minimum number of deletions, we compare these three values, 5, 5, and 2, the smallest value is 2, which becomes the result for this example. The final output is 2. Now, let's look at example 3, where the input array is nums equals 5, 1, 2, 6, and the length of the array, n, is 4. The minimum value in this array is 1, located at index 1, and the maximum value is 6, found at index 3. We normalize the indices as before, with left being the smaller index, which is 1, and right being the larger index, which is 3. Next, we calculate the three strategies. For strategy 1, removing all elements from the left to the furthest index requires 4 deletions. For strategy 2, removing all elements from the right to the closest index requires 3 deletions. For strategy 3, removing elements from both ends also requires 3 deletions. Finally, we determine the minimum number of deletions for this example. Comparing the three strategies, we have 4 deletions for removing from the left, 3 deletions for removing from the right, and 3 deletions for removing from both ends. The minimum value among these is 3. This becomes the result for this example. Therefore, the final output for this example is 3. The time complexity of this solution is O, n, where n represents the length of the input array. Let's break this down in steps. First, finding the minimum and maximum elements in the array involves scanning the entire array twice, once for the minimum value using the min, nums, operation, and once for the maximum value using the max, nums, operation. Each of these scans takes O, n, time, so together they contribute O, n, plus O, n, which simplifies to O, n. Next, locating the indices of these minimum and maximum values also requires scanning the array. Since the minimum and maximum values are already known, the operations nums.index, min, nums, and nums.index, max, nums, each take O, n. Adding these together results in another O, n, plus O, n, which is still O, n. These steps dominate the time complexity of the solution so far, and we'll analyze additional operations next. Now, let's look at the time taken for calculating the deletion strategies. Determining the left and right bounds, using comparisons like left equals min, min underscore index, max underscore index, and right equals max, min underscore index, max underscore index, is a constant time operation, O1. Similarly, computing the three deletion strategies, remove underscore from underscore left, remove underscore from underscore right, and remove underscore from underscore both, requires only basic arithmetic, which also takes O1 time for each calculation. Finally, finding the minimum of these three strategies is another O1 operation. Since these calculations do not involve any array scans or loops, their contribution to the overall time complexity is negligible when compared to the earlier O(n) steps. Therefore, the total time complexity of the solution is dominated by the linear scans, and it remains O(n). Shifting to space complexity, the solution is highly efficient, requiring only O1 additional space. This is because the algorithm works directly with the input array without creating any copies or transformations. The space used by auxiliary variables like n, min underscore index, max underscore index, left, right, and the three strategy variables is constant, as their number does not depend on the size of the input array. Additionally, the algorithm avoids using any extra data structures such as lists or dictionaries, which could scale with the input size. With no dynamically growing memory usage, the total space complexity of this solution remains 1. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive solution would involve exhaustively trying all possible ways to remove the minimum and maximum elements. This could mean iterating over all potential partitions of the array and computing their lengths, which is computationally expensive. Depending on how it's implemented, such an approach could result in a time complexity of n squared, or even worse, due to nested iterations. Additionally, a brute force method might allocate space for subarrays during each iteration, leading to a space complexity of n in the worst case. In contrast, the optimized solution reduces the time complexity to n by performing only 3 linear scans of the array and uses constant space, 1, with no additional data structures. This clear improvement makes the optimized approach far more suitable for large inputs. The time complexity of this algorithm remains n across all scenarios, best, average, and worst cases, because it always performs the same linear scans regardless of the input. Similarly, the space complexity is consistently 1, as the algorithm's memory usage does not depend on the input size. To mathematically validate the time complexity, we note that the algorithm performs 3 linear scans of the array, 2 to find the minimum and maximum values, and 1 to locate their indices. Each scan takes n, and because these scans are sequential, their combined time is n plus n, which simplifies to n. The remaining operations, like comparisons, arithmetic, and finding the minimum of 3 values, are all 1. Adding these constant time contributions to the linear scans results in an overall complexity of n plus 1, which simplifies to n. Since no additional data structures are used, the space complexity is proven to be 1. When tackling this problem, there are several common mistakes to watch out for. First, many solutions neglect to consider all possible removal strategies. It's not enough to only think about removing elements from one end of the array, you also need to evaluate the option of removing elements from both ends. This ensures that you account for the minimum number of operations. To avoid this, always compare all 3 strategies, removing entirely from the left, entirely from the right, or a combination of both. Another mistake is incorrectly identifying the indices of the smallest and largest values. If the array contains duplicates, simply stopping at the first occurrence can lead to errors. To address this, use tools like Python's enumerate or a loop to track both the values and their indices accurately. Lastly, misinterpreting the problem constraints can lead to overly complex or invalid solutions. Some may assume the array is sorted or that the smallest and largest values are unique. Instead, remember that the array can be unsorted and contain duplicates. Always verify the problem constraints carefully to ensure your solution works for all edge cases. In addition to those mistakes, it's easy to overlook edge cases. For instance, what happens if the array has only 2 elements, or if the smallest and largest values are adjacent? These scenarios can break your solution if not handled properly. Test cases like 1, 100, 1, 2, 3, 1, and 5, 5, 5 are great for ensuring your implementation is robust. Another pitfall is overcomplicating the solution. Some attempts involve sorting the array or using data structures like heaps, but these approaches increase time complexity unnecessarily. Remember, this problem can be solved with a simple n solution by iterating through the array and finding the relevant indices. The takeaway here is to focus on simplicity and efficiency, crafting your solution to handle all edge cases without adding unnecessary complexity. This problem is a great example of the greedy algorithm paradigm, where the goal is to optimize for the minimum number of operations. Recognizing that you need to explore all removal strategies is central to solving it effectively. Efficient index management is another critical skill here. You need to calculate the indices of the smallest and largest values accurately, avoiding potential bugs during implementation. Interviewers often test how well your solution handles edge cases, such as arrays with duplicates, very small arrays, or scenarios where the smallest and largest values are adjacent. It's important to demonstrate that your solution accounts for these. Additionally, achieving optimal time complexity is often expected in interviews. While sorting-based approaches may work, they generally have a complexity of O(n) log n, which is less efficient than the O(n) solution achievable with a linear scan. Strive for this optimal approach whenever possible. If you want to practice related problems, there are several LeetCode challenges that build on similar concepts. For example, LeetCode 121, Best Time to Buy and Sell Stock, requires you to identify optimal indices to maximize profit, similar to how you manage indices in this problem. LeetCode 1005, Maximize Sum of Array After K Negations, involves greedy decision-making to optimize an array's properties, which aligns with the thought process needed here. LeetCode 198, House Robber, combines greedy and dynamic programming techniques to minimize operations, making it another excellent problem to explore. Finally, LeetCode 581, Shortest Unsorted Continuous Subarray, focuses on subarray operations and index management. Practicing these problems will strengthen your ability to recognize patterns and apply efficient strategies in array-based challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. One option is the sorting-based approach, which involves sorting the array and then finding the smallest and largest indices to calculate the number of removal operations. While sorting makes the implementation straightforward, it introduces an O(n) log n time complexity, which is suboptimal for this problem. A better approach is the two-pass linear scan, which operates in O(n). Here, you use the first pass to find the indices of the smallest and largest values, and the second pass to evaluate the three removal strategies. This method is both efficient and effective, but it requires careful management of indices to avoid errors. Another option is the heap-based approach, where you use a min-heap and max-heap to track the smallest and largest values. However, this method is overkill for this problem, as it adds unnecessary space and time complexity. Ultimately, the two-pass linear scan strikes the best balance between simplicity and efficiency. Whatever approach you choose, focus on clarity, handling edge cases, and demonstrating why your solution is optimal. This will leave a strong impression in an interview setting. Great job following along. To summarize, we tackled the problem of efficiently removing the smallest and largest elements from an array, minimizing operations. This problem is a great example of optimizing computations through thoughtful analysis. Thanks for watching, and don't forget to subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!